So I remember last December 2018, I was at a Kubernetes conference, and a presentation got my attention. The presentation is talking about container security using BPF. So this is one of the slides in the presentation. So it mentioned every packet toward the Facebook.com has been processed by XDP BPF application. So I already heard of BPF before, because it's called Berkeley packet filter. Basically, I think it's initially designed for packet capture. Yeah. So there is actually a paper in 1992 talk about the BSD packet filter BPF. It's a new architecture for user level packet capture. So that's what I know of, and so I think probably most of the network engineer has used the tool called the TCP down, which is for packet capture, and it uses the BPF underneath. So that make me wonder, how come BPF could other than packet capture, how could it process the Facebook.com traffic? So I wanted to learn more about it. Yeah, so that's got my attention. So this is BPF in action in Facebook. I think Facebook, they are using a layer 4 load balancer before with IPVS, IP virtual server in Linux kernel. And so after they developed the BPF, extended the BPF, they switched to BPF and with the layer 4 load balancer, so they got a much higher throughput than the previous IPVS virtual server. So this is like their graph to show the difference. The higher one is the BPF XDP, and the lower one is the IPVS throughput performance. So yeah, interesting. Anyway, so I wanted to learn more about it, and so let's go back to how the TCP down works in general. So when you run TCP down, you give it some filter, like in this example, TCP and destination port 80 to capture HTTP traffic. So when the libpcap library take this filter, it will compile it as a virtual machine bytecode, and then the kernel takes the bytecode and to capture the packet the kernel want, and then send it back to libpcap library. Then the TCP down can read the packet from the libpcap library. And so we mostly know that this TCP down and the lib pcap part, but I think very few people know about this virtual machine bytecode part and the kernel part. So yeah, we don't know how it works. So out of curiosity, I did a experiment here. So like with this is my Ubuntu 1804 machine. So like if we the -d will actually dump the virtual machine bytecode. Let's say let's give a filter IP and the TCP, and then see what's the bytecode look like. Yeah, so like this is a simple bytecode dump, and so basically it's the LDH is load half word bytes, and so this 12 is the offset in the TCP IP header. So basically it's load the byte from offset 12 and compare it to this value, like jump equal. So if it's true, if this start from offset 12 value equals this one, it jumps to 2. If it's false, it's jumped to return 0. So this value is actually the IP protocol. Like in the Ethernet header, it has a protocol type, and the offset 12 is to specify what protocol the Ethernet payload is. So 0x800 is for IP protocol, and so like this this instruction is to load offset from 23 and then compare jump equal to 0x, which is take the the protocol field in the IP header and compare it with this is a TCP protocol number hex 6. So if it's a TCP protocol, then return some numbers, and if it's false, return 0. So yeah, that I think that's like a simple virtual machine bytecode look like. And so, but yeah, so we know, yeah, TCP down use Berkeley packet filter, but what is extended BPF they are talking about? So I go to YouTube, search the eBPF. Like there are a lot of in YouTube. If you search eBPF, and there are a lot of videos talking about eBPF, and so I dug out I went to the Let Dev mailing list to dug out the history, and so we have some mailing list record here. Say filter add. So there is like a quite of a series of discussion to introduce the extended BPF into the kernel, and this is the original author, Alexei, and patch version 10. So I believe this is the patch series they are discussing to extend the BPF feature, and yeah, add extend the BPF interpreter. So that's I read it through those mailing list discussion, and I found out, okay, that's how it's initially started. And then I also went into a company called Let-Ron, yeah, Let-Ronomy, and so they talk about how BPF extended the BPF. Actually, when I think they extended the BPF now, they call it BPF because the classic BPF that TCP town wants to use is also transparently translated to extended BPF, eBPF. So now actually there is no more classic BPF. They all call it BPF now, which is actually extended BPF. So when they talk about this new extended BPF, how it works, and so basically it shows in a user space, you write a C program and use this llvm compiler to compile it to an object file, and this object file is a bytecode. So then you load this bytecode to the kernel through a BPF system call, and then in the kernel there is a verifier which is to check if this bytecode is safe to run or not in the kernel. So if it's not safe, it will reject this bytecode, and so if it's good, safe, and it accept, the verifier will accept the bytecode, and if you runs on a x86 machine, then there is a just-in-time compiler will compile the bytecode to native x86 machine code, and yeah, so that's how the program is loaded into the kernel to run, and yeah. So there are another talk in Docker conference, a company called a community actually called Signaling for container network and application security. They also use the BPF for container security, and again, you have a C source file, compile it to bytecode, and then inject into the kernel verifier, and just in time to compile it to a native code. Yeah. So what is a XDP? So XDP is Express Data Path. It's one of the feature of BPF. So how it's like in kernel, when normally when a driver take a packet, it will allocate a socket buffer, and then send it to network stack, like the kernel TCP IP stack, and then through socket the socket, and then send it to the user space program. So this is a lot of work, and the performance is not very good. That's why some applications, if they have higher performance requirement, they will use kernel bypass driver like DBDK to to work around the kernel stack performance problem. So this express data pass is actually, it's not a kernel bypass. It's actually still use the Linux kernel driver, but right after a driver take the packet, you can inject a eBPF program and examine the packet, and if you don't want the packet, you can drop right in the driver before allocated the SKB memory buffer, and then send it to TCP IP network stack. So this is quite efficient, and I think that's how Facebook use this XDP, eBPF XDP for their layer 4 load balancer. So in order to support the Express XDP, the driver has to support the XDP, and so right now there are a couple of driver Linux kernel driver support XDP, like the Intel iXGB support the XDP. So if the driver does not support the XDP, there is a driver called generic XDP will work, but it is the performance will be not as good as the driver that natively support XDP. Yeah, so this is like native generic XDP driver is after the driver layer. So this is like a core stack for XDP. As you can see, if I think yes, so the virt.io net driver also natively support the XDP. So in the driver, after before the SKB library, before the SKB memory allocation, it either drop the packet or pass the or redirect the packet or pass the packet, which is come to pass to the network stack normal pass. And so if the driver does not support XDP natively, then this is where the generic XDP driver comes in, and before the traffic ship ingress and the letter filter ingress pass. So yeah, so this is how the core stack look like. So that's a pretty quick introduction, and the BPF, eBPF, XDP is actually a very complicated topic. So yeah, I just started to learn this topic, and so I come up so here is someone. So I read an article from Red Hat developer website. So a developer, he used the eBPF to troubleshoot a network issue, and he had an example. To change the TCP packet flag. And also change the ICMP TTL value. So I steal his sample code, and just want to see how it works, how the eBPF XDP works in a Linux kernel. So I downloaded GitHub, and I have a program here. It's called a TCP ACK. Basically, what it does is to drop packet, randomly drop a packet when the ACK flag is on. So like you can use TCP BPF trace print key to trace to debug the BPF program. So this is like a BPF C code, and you compile it with clang, which is a front end to LLVM compiler toolkit, and you compile it to a object file. This is the object file. Then after you compile the object file, you can load to a network interface. So, for example, if I want to load to, this network interface with the XDP eBPF XDP program, and I use the IP command from IP route package, IP link set def eno2, and XDP object file is the TCP so this is to load the BPF the bytecode, attach the bytecode to this network interface, and this verbose command parameter argument will output the actual bytecode. So this is the bytecode here. So all those R0, R2 is the register. The verifier in the kernel dumps those this bytecode, and it says it is safe to run this bytecode. So how do you know if it's attached to the network device? You can see so after here you will see a XDP here, string here, and also it also gives you a XDP ID number, and also show you if it's JITed. So JITed it's compiled into native code. Also in Linux kernel source file there is a tool. It's called BPF. It's called a BPF tool, and you can list all the BPF program running in the kernel. So there are someone. It's called a C group control group SKB. I think this comes with Ubuntu 18.04. I don't know what they are for, but that comes with Ubuntu 04 default installation. So this one is the one I just loaded, and you can use this BPF tool to dump the xlate translated. Is the to dump the bytecode. Give it the ID 59. So it will dump the bytecode. You can also see the native code, GTD code. So this is x86 GTD code. Yeah. So those things, these things are hard to read, and yeah, I don't know if I have time to learn those stuff. And yeah, so we attached to the network device, and this code is to randomly drop a packet every ratio. Drop a packet, because I return one here is so like in this here I call the program TCP ACK, and then it will return XD drop. So XDP drop is to drop the packet. XDP pass is to pass the packet to the kernel let stack. So let's run a test to see if packet is dropped. So if I run a TCP down here. So on the same Ubuntu machine, so when it receives the packet, it should drop some packet randomly. And on the same machine, I will request the so this is a server side. This is the web server side. I will also run TCP down, and this is the receiving side running BPF XDP. So when it receives the packet, it will drop the some of the packet. And let's do the. So we get a web response, and we have a TCP down here on the same machine. And so how you can tell there is a packet drop. So for example, here, this is this machine receiving side receive a payload from the server, and it's act some packet, and but also come with a TCP option SAC to selectively act some frame, which means there is a packet dropped, and so say if I have a Wireshark, maybe make it easier to read. So this is a sample capture, and the client send a GET request, and the web server act the GET request, and then the web server send a packet. But it also gives you a previous segment not captured, which means the some of the packet is dropped. It's dropped by the XDP program, and so this is like the receiving machine, Ubuntu receiving machine, ACK with if you go look at the TCP option, it has a SAC, say it's ACK from this sequence to this sequence because the packet is dropped, right? So this sequence is 489 and 1952, and this receiving machine ACK that this packet, but we don't know, but the previous packet is dropped, so that's why the TCP down cannot see it. So here is the out of the order packet. This is the dropped packet. I think, you know, sometimes the Wireshark interpreted the packet, it shows it's out of order. It's actually not out of order. It's a retransmitted packet from the server because the previous packet, same packet was dropped by the XDP. So how you can tell it's a retransmitted packet instead of an out of order packet? The way is like from the server. This is both from the same server, right? Both packed from the same server, and you can look at the IP ID identification number. So this is a previous one. This is one that was dropped but retransmitted before this one. So, but this one, it has a IP ID 39211. This one has 39203. So this one has a higher IP ID number than this one. So this is actually a new packet generated in the server and retransmitted this this packet with the same TCP sequence. So you can look at the TCP sequence. Right, sequence number from 61 to 244 that was dropped. So, but the Wireshark look at it as out of order. It's actually not out of order. It's retransmitted because the previous one was dropped. Yeah. So that is a quick demo how the XDP BPF XDP works, and hope you learned something. Yeah.